On we go with more content on memory. Welcome back to Cognitive Psychology. Last time we talked about a lot of the standard theories of memory stages, right? Sensory memory, short-term memory, and long-term memory. We've also kind of looked at some of the critiques of the long-standing idea of short-term memory and how it's been replaced with the idea of working memory instead, and all of the details of Baddeley's working memory. But now what we want to do is we want to shift more towards I think what we could call long-term memory. It's not a clear-cut distinction, but this idea of memory systems, as I have it here, um, there's a lot of research. A lot of this goes back to at least the 1970s with a guy named Endel Tulving. And Tulving had a lot of ideas about the different kind of forms that memory can take. It seems that we have different kinds of memories, right? And so how many different types or kinds or formats of memory are there? This is what the whole question of memory systems boils down to here is how this might look. And so we could possibly go a little wild when it comes to trying to just intuitively figure out how many possible types of memory there are. And maybe some theorists have gone a little overboard there. So we'll try to keep it simple as we can. One thing I'm going to do is start with a key distinction here between what is called explicit memory here. And on the very next slide, to jump ahead real quick, we have implicit memory here. Now, under each one of those headings, we can have some subtypes here, and I'll kind of unpack it a little bit, but I don't want to maybe linger too much over some of the subtypes. But explicit memory, what is that? We're defining that here essentially as memories that you can recall. Now, that's not really a good definition of memories. Presumably, we can recall all memories, but I think under that definition of declarative memory, conscious access, and recall, that's kind of a critical definition here of explicit memory. The reason we use the term explicit is the idea is that I can just explicitly think about this particular idea. I might have used in a previous video a question on whether or not you can tell me what you had for breakfast this morning. So the idea is that if I can think back to earlier this morning and I can clearly remember, oh, yes, I remember. I made toast and I scrambled 2 eggs. That was my breakfast. That was really my breakfast today. So, and I know it's recent. It's just happened today. I know exactly what I did. That's an explicit memory because I can visualize it. I can remember. I can see it in my head, standing at my stove and scrambling the eggs and so forth, and what pan I used and all of that stuff. Um, and of course, I can verbally tell it to you or anyone else, right? I can state it. That's what I mean by consciously report. So that's also a declarative fact, right? I'm declaring the fact that I had toast and scrambled eggs for breakfast. So that's the kind of thing we'll call an explicit memory here. Another example of an explicit memory that I might have used in a previous example was remembering where you parked your car when you go to something like a shopping mall, or even if you come to campus and we have all these mini garages and so forth. I think I brought that up when talking about the rehearsal stuff, right? That we don't necessarily spend a lot of time and effort in rehearsing to try to memorize where we parked our cars. We just sort of park and then go about the rest of our day doing things. And then when it comes time to go back to your car, well, you just go back to your car. You just remember, right? But if you let's say you did this at the mall and we're in the middle of the mall and someone were to ask, "Oh, where did you park?" You can probably say, "Oh, outside of such and such store." So again, you're declaring this as a fact. It's an explicit memory. You remember exactly where you parked your car in relation to, some entrance to the mall and what store it is, right? So these are all explicit memories, right? And you can declare them, so that makes them declarative memories. You can also have memories for episodes and events. This is something that came up when talking about working memory. The idea is there's an episodic buffer in working memory, but it connects to episodic long-term memory. So I can remember past experiences, right? I think I probably talked about the emotional impact of flashbulb memories and like memories of things like the 9/11 terrorist attacks, right? So remembering the details and where you were and how events unfolded, those are all episodic memories. Um, if I can remember any significant event from my life, maybe taking a trip somewhere, I might be able to remember certain events and things people said. Maybe I can remember going to a concert a few years ago and how, and some of the things happening at the concert. These are all episodic, right? But also they're explicit because I can describe them, right? So I can say, I went to that concert and the band started with this song and so on and so forth, right? So I can describe it, and that's all makes it what makes it explicit. Semantic memory then is our name recall of basic factual information here, right? So the fact that I can remember somebody's name, I remember certain facts that I learned in school, that's all semantic memory, right? The meaning of words even is also part of this as well. One of the things that makes the study of explicit memory a little bit interesting, at least, is the kind of effects that involve amnesia, right? So amnesia, memory loss. Um, there's two kinds of amnesia. We can briefly talk about them. I don't know that it's useful to really dive into the types of amnesia too much here, but you may have heard of this before, maybe from a physio psych course, a clinical psych course, or even an introductory psychology course. Anterograde amnesia and retrograde amnesia. So retrograde amnesia is what most people think about when you think about amnesia. It's the kind of amnesia that gets depicted stereotypically in cartoons or soap operas or whatever. Someone gets a bonk on the head and suddenly they forget their past, right? And by the way, that's not really going to happen in most real life situations. It would require a significant trauma to the brain to forget your entire life history, right? That you wake up from a head injury and you don't know who you are, you don't remember your own name, you don't know anybody, your family and friends or anything like that, and you can't remember where anything about your autobiographical life history. Not likely to happen, right? But what can happen, in very somewhat more commonly, is let's say you have a concussion, right? Could be a sports concussion, a severe one, maybe even knocks you out and causes you to lose consciousness. And what might be observed is that you can't remember that happening. And maybe you don't even remember. Let's say it was in the middle of a football game, and so after recovering, later that day, you might not remember even being at the game. So that means that not just the moment of the concussion, but maybe even for a couple of hours leading up to that, your memory of that might be very, very hazy or just mostly not even there at all. So that's a form of retrograde amnesia because what's happened is you have forgotten some things that occurred prior to the concussion, right? So it's memory for the past in that sense, right? Past in relation to when the injury occurs, right? By the way, my abbreviation PT here, that stands for patients, right? So the patients can't remember these experiences from the past, right? Anterograde amnesia, though, is refers to our memories for things that occur after the injury. This is most famously studied by the patient known as HM. And so, what happens with HM is he has a surgery because he has severe intractable epilepsy. And by removing a portion of the damaged temporal lobe and the hippocampus, which sits just below the temporal lobe, HM experienced both retrograde amnesia because some of the loss of the temporal lobe areas were important for that, but also, and this was maybe somewhat unexpected, pretty severe anterograde amnesia. So now what happens is that HM cannot form new long-term memories, and this is now a permanent thing for HM, right? Not just a temporary thing, that can also happen from a concussion. Not just that kind of short-term retrograde, but even some short-term anterograde amnesia happens following concussion sometimes. And but now the idea is that for HM missing the hippocampus, he will no longer be able to create new long-term memories. So he can get a new doctor, right? And a doctor comes to visit and observe and HM and ask a few questions and interact with him for an hour or so, and then a couple days later, the same doctor comes back again, and HM will have no memory of having ever interacted with that person ever before, right? They can't create new memories, or he couldn't, right? But what's critical here is that these forms of amnesia, either one, anterograde or retrograde, seem to primarily target explicit memories, right? So the explicit ability to report, what happened to me in the hours leading up to my concussion, have trouble with that. The explicit ability for HM to report having interacted with some person that he had never knew until after the surgery was performed. Again, he cannot do that. But what about other things? So on the right-hand side of the screen, I have a task here. This is a kind of task that researchers studied use with HM quite a lot. This is called the star drawing task. So as you can see on the little piece of paper here on the platform, the tablet, there are two stars, one within the other, and your task is to take a pen or pencil and trace a line between the two stars. So you're drawing the star as well, but you have to trace it so that you keep your coloring inside the line, so to speak, right? But as you can see here, there's a little black occluding surface here that prevents you from seeing your hand while you do it, and rather you can only see your hand as reflected in the mirror there on the right. So in this case, it's a challenging kind of a task, but you can practice and you can get better at it, and that's really what's crucial here is is that HM, when first given the task, will perform just like any of the rest of us. We're going to make some mistakes. Our lines are going to kind of squiggly and move every which way. But as you do it a second time and a third time and a fourth time and so on and so forth, you get better and your lines get straighter and you do it a whole lot nicer. So we can do this. We can give HM an hour's worth of practice on the task and he'll get better. So that shows some embedding of some kind of memory, right? But what's critical here is that now we're going to take the whole contraption away and we're going to bring it back another day. So maybe just wait one day. We'll wait 24 hours. And then we set up the task. And the first thing we can do is ask him, you remember performing this task before? He's going to say, nope, I have no memory. I've never seen this thing before. What do I do? So you give him the instructions, right? And then does he return to his previous baseline performance as if he had never done it before and he has to relearn all over again? No. His initial trial is actually really, really good. And he returns to this high level of performance really quickly. And again, we do this a third day. On the third day, we ask him, do you ever remember doing this before? And again, he says, nope, never seen it. And so we ask him to start, learning it. And he's really good right from the get-go by the third day. So this is now showing here that whatever kinds of knowledge and memories are being encoded into the brain as relevant to performing the mirror drawing task are seem to be separate from his explicit memories of ever having performed the task before. Another good example that I really kind of like from an everyday perspective is riding a bicycle. You could a lot of people learn to ride a bike when they're children, 5, 6 years old, let's just say. And so what's going to happen is what do you do when you get on the bike, right? What is it that you're learning? Well, you get on the bike and maybe someone's helping you. They hold on to the rear of the bike and the handlebars and they get you on there and you start pedaling and steering and they're kind of running alongside you, holding you up, and then they're going to let go, right? At least that's how I remember it being done back in the day. And so then what happens is that when they let go, maybe you are able to stay up for a few seconds and then suddenly you tip over and crash. So you get back up and you get back on it and we repeat this all over again. And then the second time, maybe you're able to keep going a little bit longer before you crash. And then you just keep doing this over and over again until you just don't crash anymore, right? And then you just kind of have it. And so at this point, we would say, what is it that you have learned? What is it? What happened in your memory and in your knowledge between the point at which you crash every time somebody lets go of the bike versus when you no longer crash and now you seem to have mastered it. Sometimes we might say things like balance, but that's really not enough because riding a bike really requires that we have to be pedaling forward and making small adjustments with the handlebars the whole way. And what we're doing is we're actually harnessing a phenomenon known as gyroscopic precession, right? So we are harnessing gyroscopic dynamics to ride a bicycle. But as a 5 or 6 year old, you don't know anything about the physics of gyroscopes, right? You simply just are riding your bike. Let's imagine that we have a patient who learned to ride a bike as a child and then has that kind of stereotypical cartoonish retrograde amnesia as an adult. And so we could ask them, do you know how to ride a bike? And they will say, well, what's a bike? No. But they're going to say, well, I have no memory of ever riding a bike, right? So all of this stuff, maybe they were trained, but they can't remember that specific episode now. Their explicit episodic memory is gone, right? But we'll say, well, hey, let's see. And we're going to put them on a bike, and we would expect that they should just be able to ride without much effort, without much trouble here, because even though their episodic memory is gone, the actual skill that was acquired and stored is still preserved, right? And so this kind of skill acquisition that we see in HM with the mirror drawing task, or when it comes to something like riding a bicycle, and there's that old adage, right? It's like riding a bike, you never forget. It's kind of this issue, right? These are different kinds of memories and different kinds of knowledge. They are not explicit, they are implicit, as it turns out, and we cannot describe them, right? So if I were to ask you, what do you know about riding a bicycle? You're not going to start giving me a dissertation on gyroscopic dynamics, right? It's not as if you somehow intuited the whole physics of gyroscopes in that one instance where you now have suddenly mastered bike riding, right? This is the kind of knowledge you can't declare, right? You have learned something here, but I can't sit down and tell you exactly what it is other than saying, I'm staying balanced now and I can ride the bike. That's about as best as we can do to describe what we know about riding a bicycle. So there's a lot of other stuff going on than at a more implicit level, right? And that's what we'll use this term for. Implicit now means that I can't really describe it to you and talk about it, but I can show you, right? Show, don't tell, right? So that's what we have with implicit memory here. Non-declarative, more procedural in nature. So procedural memory is another term that gets used a lot to describe the fact that there are certain procedural steps involved in the task, whether it's the mirror drawing, riding a bike, or even playing musical instruments in many cases. A lot of interesting cases, by the way, of musicians who, in later years, develop memory problems like Alzheimer's disease. And we find in some of those cases that their musical skills are remarkably well preserved, even when they are starting to have lots of severe explicit memory impairments. In fact, the musician Glenn Campbell, his family made a documentary about his challenges with Alzheimer's disease prior to his death, and they even mounted a final kind of farewell tour for him. And very unusual things would occur during his performances. So his ability to sing and play the guitar still at a very high level was still there. But he would do things like play one song and then play a couple other songs and then repeat a song from earlier in the set because he had forgotten that he'd already done the song. So the explicit memories are really, really starting to fail here. But the implicit skills that he had honed from a whole lifetime of being a professional musician were still largely intact, right? Here's another example of some implicit stuff, these semantic priming studies here. So this kind of shows some subtle effects that I think are a little bit interesting. So over on the right here, this little text box on the right, we're going to show Ps, that's participants, a list of words. So these words could include words like elephant, perhaps, right? So if this person is someone like HM, maybe they have anterograde amnesia, then after I show them the list of words, I'm going to ask them, tell me the words. And they're going to say, what words? I don't remember the words, right? So then what we're going to do is we're going to have them perform next what's called a stem completion task or fragment completion. Stem completion is the first one. We have 3 letters, ELE, and then some blanks, blank, 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 blank. Fill in the blanks and tell me the word. And you might guess the word is elephant here because I said it, of course. Now, even if I hadn't previously primed you with the word elephant, you would probably still figure it out. But what we can do is we can determine reaction times here, right? Let's imagine we use this with just normal control subjects who have no brain damage here, and I prime them with a list of words that includes the word elephant. So then when they see ELE, blank, 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 they'll quickly fill in the word elephant. If I have another kind of control group that is primed with a different list of words and it does not include the word elephant, they will still figure it out, but they might just be a little bit slower. So the extra kind of speed increase in their reaction here to perform that response might be a little faster because of previous exposure to the word elephant. What about that second word? This is the fragment completion. So now it's just blank O blank US blank. Notice that there's at least two possible solutions here. It could be the word robust, or it could be the word locust, maybe others as well that I haven't thought of. So now what happens is that, it could be 50-50 in terms of which one of those two our subjects might pick. But what if, again, if we have HM as our patient and we show the word robust in the priming list, then he is far more likely to fill in the word robust when doing the fragment completion task, even when he doesn't explicitly remember seeing that word in the list. So again, this is more of an implicit effect. I am also mentioning that we can also use backward masking here. So we've covered masking before, where you present a stimulus on a screen, and then it is immediately replaced with some other kind of masking noisy stimulus, and it kind of prevents you from explicitly saying what it was. So we can show the word robust followed by a mask. And if we ask people to consciously label the word that was present, they're not likely to succeed here. But then later, when they perform that fragment completion, they're still going to use the word robust instead of locust, right? So that's again showing more of an implicit influence on their performance in this task. One other form of implicit knowledge here comes from perceptual skills and perceptual learning tasks. One example of that is prism adaptation research. This has a long history in perceptual learning research. The way this works, hold on a second. Took me a long time to find my prism. Uh, Too many bookshelves. This is a prism, right? So this is an optical wedge prism. And these sorts of things can be mounted on like lenses on glasses, right? And the way this would work is you might be looking here. So we'll put this. I'm going to cover one eye, and I'm going to put this over another eye. We'll pretend it's mounted on some goggles or something here. And what this does is it bends the light. It bends the light by a fixed angle. So that way, what happens is that if I hold some object up in front of me, like my pen here, if I'm looking at it through the prism, it's going to make the object appear to be shifted to the side by some fixed angle. So when I reach for it, I'm obviously going to aim for where it appears to be. And I'm going to discover, of course, that I'm missing it quite badly because it looks like it's over there, but it's really right in front of me. So we will adapt, right? It doesn't happen right away, but gradually over, say, 10 or 15 repeated trials of reaching, I'm going to aim my hand back to where I started. But then what happens is once you remove the goggles, you might think that, oh, we just would go right back to normal pointing. But instead, what we see is something called a negative after effect, right? And in the negative after effect, you might do something like hold up the target again and say point to this, and now what happens is that you're going to kind of aim to the left of it. You're going to miss it, right? So it's an after effect because it's an error that persists after the prism exposure is ended. But it's called a negative error because your mistake is now in the opposite direction as the original mistake, right? In the original beginning of the session, you're reaching to the right of where the target is, and now you're reaching to the left of where the target is. And this will persist for several trials, and now you have to kind of readapt back to normality here. And of course, what we can see is that, again, referring back to people with in some form like patient HM, they can still acquire prism adaptation effects here, right? So it's dependent much more on an implicit process, not any kind of explicit perceptual statements here. Okay. Moving on to some other types of memory systems here. We've had a lot to say in the past about imagery, right? When we covered the perceptual chapter, we suggested that perception is in the business of creating mental images. And certainly, of course, that's another kind of memory that we have is that I can have this kind of visual spatial pictures of things, right? I can visualize objects and what they look like. I can close my eyes and think about an apple or an elephant or anything like that. I can even remember people's faces and what they look like, and I can remember my childhood home and what all those what the house looked like and in the rooms and the furniture and all that stuff, right? So it's almost like I can see these in my mind. So that becomes maybe another kind of memory system here as well, a perceptual memory of a type that is more explicit, right? So we'll call those mental images. As we have also suggested when previously talking about imagery, this is thought to play an important role in visual spatial tasks like the mental rotation task I have in the top right-hand corner, and also the mental travel task, also shown there, where you're asked to imagine traveling from one place to another on this imaginary island. And so you get a chance to look at the island for some period of time, and then it's removed, and then you have to mentally travel from one landmark to another. And the time it takes to mentally travel is then shown to map proportionally to their actual spatial layout on the map. So that seems to be another kind of memory as well. But as we have previously noted, aphantasia is also a thing, right? People report that they do not have distinct and clear mental pictures like this. And by all accounts, people with aphantasia still perform the rest of cognition completely normally, right? They perceive and act normally. They can perform mental rotation tasks, and so they can do all of the kind of stuff. Their time to perform some of the tasks might be a little bit different, but they can still successfully do it. So in this case, it's a little bit of an unusual phenomenon here that we might want to consider calling this a particular memory system, but at the same time, it's not one that necessarily everyone has. Now, when it comes to spatial knowledge, we can sometimes move away from the kind of explicit imagery that we're defining here, and maybe talk about it in more implicit terms. I forgot to mention congenitally blind persons. Let's mention that real quick. That's the picture on the right. So this painting was done by an artist named Ezraf Armagan. And what's really interesting about Ezraf is that he was born blind. So a lot of people who have visual impairment are not born blind, right? They have past visual experiences, so they kind of know what the world looks like before they end up losing their vision later on. But Ezra being born blind, there's a lot of aspects of this spatial nature of visual perception that he would have never experienced. And that includes things like perspective, right? Linear perspective and texture gradients and the kind of things you learn when you learn how to draw in perspective. And he can draw in perspective. As you can see, this is one of his paintings here. And we have this bridge going over some body of water here. And we've got trees and flowers in the foreground and trees in the background. And they all show appropriate perspective. And he claims to have never been taught explicitly perspective. He seems to have intuited it and taught himself how to draw this way without ever having any visual experience. So I find this a very compelling form, apparently, of mental imagery, right? He seems to have strong visual imagery despite having no visual experience ever and not even having functioning eyes at all. So it's another wrench to throw into this whole picture here. Now, back to what I was about to move into with maybe a more implicit way of thinking about spatial knowledge here. So we can think about this idea that we might call a spatial map or a cognitive map, right? Our understanding of the spatial layout of the world around us and how to navigate. We navigate all the time. We navigate around our own homes. We might need to navigate around campus, or if you're driving around town, Orlando or anywhere else, you have to navigate those streets and you know where they go. We do have some good solid evidence that in the hippocampus, separate from all of the stuff that is important for embedding new long-term memories, there are also what are called place cells that tend to be active when we are navigating in specific locations. And this seems to suggest then that the organization of the hippocampus is important for spatial knowledge. We find that these kinds of regions are active even in rats when they're learning to solve mazes. We also find that in some animals that are migratory species, like some birds that have to migrate really long distances, that this region of their brain is enlarged compared to other birds that are not migratory. So suggests it plays an important role in this kind of knowledge. But when we think about the kind of spatial knowledge we have, we might want to think about two kinds, right? So what I have here is what is called uh, allocentric space and egocentric space. So what is that? Allocentric space represents my ability to kind of visualize a three-dimensional space. Like just think about a room, like my office behind me. I can visualize the four walls and the floor and the ceiling and where the bookshelves are and where the chairs are and everything. And I could close my eyes and I can just visualize this whole thing. And it's like I'm not even there, right? It's just like I'm seeing this kind of 3D depiction of the whole room. And so we'll call that allocentric. Allocentric refers to a kind of having a point of observation that is external to the scene and separate from the scene. Uh, and separate that from egocentric. So egocentric means now with reference to the self, right? It doesn't mean I think I'm better than anything, or like it just means centered on the self. So one example is if I were to ask, here I'm going to grab my pen again, and I'm just going to put it on the table. You probably can't see it, but I could ask, where is that pen in this room? And if I were to adopt an allocentric perspective, like maybe let's say I walk outside of the room and someone were to ask me randomly, where's that pen? I can describe it in allocentric terms, right? I can say it's on the table that's on against this wall to the right of where my computer is set, right? But when it comes to doing something like reaching for it and grabbing it, I need that in egocentric terms, right? I need to know where it is relative to me so that I can get my arm going out there to wherever it happens to be and interact with it. And so we'll call that perception in action, right? That is my immediate perceptual experience of where things are and the kinds of actions I can perform with those things. That seems to be more of a egocentric frame of reference, and that might be more implicit here. So again, this would suggest that my ability to exactly label where things are in allocentric reference frames is distinct from my ability to just reach out and pick things up. And there is some evidence that these are, in fact, associated in the brain. If you've ever heard of people talk about the two-channel stream of vision, the dorsal stream, which is called the where and how, or how channel, versus the ventral stream that refers to the more kind of what channel, that kind of maps a little bit to explicit versus implicit memories here. The ventral recognition what channel is more explicit, and the dorsal where and how channel is a little more implicit, driving perception and action. Another form of memory, I mentioned this briefly talking about explicit semantic memory was here as well, but there's a little more detail to unpack on semantic memory here. So semantic memory involves word meaning, right? That's what semantic means in general, is meaning. And so according to this idea of a semantic network, we store meaning in kind of interconnected nodes here, right? So we have here on the bottom, I have a network, right? So at the center of this network is a node for the word bitter, right? And bitter has a few different meanings, but one meaning is that it reflects a taste, right? One of our primary tastes, like sweet, sour, salty, bitter, and so forth. So I could interconnect bitter with some of those taste sensations, and that means I'm going to have linkages, right? And that's what the lines are that connect these different nodes, is how closely it links to that. And separate from the other taste sensations, I might also even think about what are some of the things that actually taste bitter. So beer becomes our nearest node in the network here. And because beer is an alcoholic beverage, I might have some other connections to other kinds of things, lager, wine, sherry, get all those connections in there. Got wine connected with cheese because that's a popular pairing. So in this case, we start to see how the semantic network kind of branches out based on similarity of meaning and other associations that we have between ideas. Likewise, bitter also can be used to describe an emotion. So now we might connect this over here to another emotional network that's kind of kept separate from the beer, wine, and cheese network, right? So here we can see then that and according to this view, this is how our memory is organized, right? It's a very complex, interconnected network full of nodes. Each node represents an idea, and its connections to other nodes represents its similarity to those ideas, and the length of those connections is also important, right? So it might be that the way this is drawn here with a short linkage to beer and a longer linkage to resentful could indicate the idea that, at least for the persons who's represented by this network, is that maybe they more often think about bitterness as applied to beer as opposed to an emotion, right? So, but of course, in another person who spends a lot of time thinking about emotional states, maybe those linkages look a little differently, right? So there's some individual differences into how these things would be organized, and that's a function of your understanding of word meaning as well as your own experiences with these interconnections. On the right is a jumbled mess of a semantic network here, but I include it because it kind of nicely illustrates something a little more realistic compared to the simplified network here on the left, right? Having a complex set of interconnected nodes that, in terms of how this would actually look in real life human knowledge, is going to be a great big old messy network, right? So we can imagine it this way as well. What's also relevant to this concept is the idea of spreading activation. So if I think about the word bitter, the idea is that's going to activate, it's going to send some energy and some activation to that node for bitter, but some of that energy is also going to spread out over those linkages, and it's going to make me think of things. And is it going to make me think of beer? Maybe if that linkage is close, right? If that activation spreads across to beer because it doesn't have very far to travel, is it going to make me think of resentful? Again, it depends on the length of that node, or the length of that linkage between the nodes, I mean. Okay, another thing to talk about here with memory systems is another way of organizing knowledge, just not now on a kind of in a spreading network model as we had previously, but now more of an organized kind of hierarchical level of organization here. This is good for accounting for certain kinds of categories. Now, the network model had categories in it. We had alcoholic beverages on one side, we had emotions on another side. Those little clusters of nodes could be ways of thinking about how categories are organized. But the work here of Eleanor Roche and colleagues explains this more in terms of hierarchical structures here. So she defines three levels in the hierarchy: superordinate level, basic level, and subordinate level. So what are we talking about here? Let's talk about dogs. I have that as an example at the bottom. So the word dog is called the basic level because it's just a familiar everyday term that we use to describe dogs, right? Now, at the superordinate level, that means at a higher level. And so we might say that dogs are mammals, or they are animals, right? Or vertebrates, right? There's lots of different kinds of superordinate levels. But if I were to see a dog on the street, I'm not going to look and say, hey, there's a mammal, or hey, there's a vertebrate, or there's an animal, right? I'm going to say, hey, there's a dog. So that would suggest the basic level is the one that we just naturally work with most of the time. The subordinate level is to identify something like the breed, right? Like, oh, hey, there's a Australian Shepherd over there, and so, but we might do that, but in many cases, probably we don't, right? So the way that Roche did this was to have people categorize items by answering these kinds of questions, and those questions were framed at either being superordinate, basic, or subordinate levels. So if you're shown a picture of just like a comfy chair from a living room, right? I could ask you, is this a piece of furniture? You're going to say yes. I'm going to say, is this a chair? You're going to say yes. If I say, is this a living room chair, as opposed to say the kind of chair you might find in the dining room or in a classroom or whatever, again, you're going to say yes. But obviously you say yes to all of these correctly, but we're interested here in the reaction time. And so what we find is that when the question is framed at the basic level, is this a chair? Reaction time is fastest. When you have to provide an answer at the superordinate or at the subordinate level, it's like it gives you one extra thing you have to think about. Like, okay, I know it's a chair, but that's a living room chair. Yeah, okay. Yes. So a little one extra little level, so when you first see it, you're operating just at the basic level of chair, and if the question asks you about furniture or living room chairs, you have to shift your thinking to those other levels, and you're going to be a little slower to respond, right? So that's a consistent finding that Rush gives us here. But one of the other interesting twists that she did in this work was to look at expertise. So she brought in bird experts. That is, people who are like, bird watchers who really have invested a lot of time in learning how to recognize different species of birds. So we're going to show them pictures of birds, and we can ask them at the superordinate level, is this an animal? They'll say yes. We can ask them at the basic level, is this a bird? And they're going to say yes. But if we ask them at the subordinate level, is this I don't know, a Florida scrub jay? All right, now we get to the subordinate level, asking it the specific species. Um, well, if they recognize it as such, they're going to say yes, right? And what we find is that these bird experts actually do better at the subordinate level. It's as if something about becoming an expert on birds has shifted the way in which your mind operates from the basic down to the subordinate. Now, this is not something that's universal for all kinds of categories because when the bird experts were shown pictures of dogs, they're just like everyone else. They're going to do better at the basic level. If we ask them, is this an Australian Shepherd? They're going to be a little slower. So bird experts are experts at birds, and therefore they shift their functioning to the subordinate level only within their area of expertise. So it's an interesting finding there when it comes to how we work at these different levels, but it's also kind of an interesting insight into the nature of expertise in general, that it seems to, at least in this respect, change the level at which you operate with regard to that particular topic. Right. Last thing we want to say here about memory is just about the encoding and retrieval stuff about the hippocampus, since we were already talking about HM. So, as we learned with HM, damage to the hippocampus affects encoding into the temporal lobe. And other further damage to the temporal lobe is going to cause the retrograde version of that, losing some of the memories that were stored there by the hippocampus. This connects to what I was talking about with that two-channel theory earlier, because that I mentioned the ventral stream that carries information about what things are and is connected to explicit performance. That involves the temporal lobe of the brain, and so damage to that is going to affect these kinds of amnesias here. Whereas the so-called dorsal stream that involves the where, what, implicit kind of stuff, that involves more the parietal lobe of the brain. So damage to the temporal lobe does not impact performance on the spatial tasks, right? A few other things we want to talk about. This is maybe a topic better reserved for physiological psych type courses, so I'm just going to gloss over it here, is that in order to store a memory, this would suggest that we have to cause some kind of change in the brain, right? That at one point in time there's something I don't know, but then I learn it, so now I know it. So that would suggest that something in the brain has changed. And so how do we do that? How do we change the brain so to make room and store something new and then stabilize that memory trace and make it reliably something that we can access? This is called long-term potentiation. It involves actual metabolic changes at the level of the synapse that change the sensitivity of synapses. So if you recall some things from basic intro psych or physio psych about axons releasing neurotransmitters which stimulate receptors on dendrites, the idea is that metabolic changes to the axon can influence how much neurotransmitter is released. Metabolic changes to the dendrite can regulate the growth of receptor sites and change their sensitivity to incoming neurotransmitter signals. And so this idea that repeated activation of a synapse, like if I repeatedly have the same experiences and then I'm going to encode that as a memory the more often it happens, or if I repeatedly recall and access this memory and think about it over and over and over again, that's the kind of repeated activation of certain synapses that is now called long-term potentiation. Historically, it's also called Hebb's law, which is best summarized as the phrase, neurons that fire together wire together, which is just a shorthand way of saying that repeatedly activating these two neurons together through their synapse causes them to sensitize with relative to each other here. Okay, well, now we have covered this chapter. It's a little bit briefer, so I tried to do this all in one one video here. So hopefully this will set you up for our next exam. And if you have any questions, of course, as always, let me know.